let's record. Here we go. Exercise 13G. So now we're tying it all together. You've done some algebra. You've learnt the log rules. You've learnt how to solve using log rules. Then now we're looking at log transformations and graphs. So same thing as usual. This is your log. Base could be any base number. But again, all that transformations I taught you in chapter 7 still applies. Let's recap. What does D do again? Can I please have Namafi? What does D do to the graph? When you add on something, what happens to the graph? Up or down? Still the same. Up or down. And then whatever you're logging, so normally it's log of some base of a certain value or log X. Whatever you're logging is going to determine what again? So in this bracket here, what does that determine again? Anyone remember? Hands up if you remember. Left or right? And there's also another thing too. Dilation, very good. So there's two that you learnt in chapter 7. There was translation, but it was horizontal translation because it's dealing with the X. And there is also a dilation, but a horizontal dilation, which means a horizontal stretch. We normally say dilation from which axis again? Y-axis, because remember, moving your hand, if it's moving horizontally away, it's moving away from the Y-axis. Yeah, so Y-axis here. So when you move your hands horizontally, you do a horizontal stretch. It should be dilation of factor, whatever it is, whatever the factor is, from, which is the key word, Y-axis. Which one governs the dilation? N. N is the dilation. That's how much you do the stretch. X plus C, the C is what determines left or right. The way I taught it though, as I said, let the entire thing equal to 0. So if you let N bracket X plus C equal to 0, and then you solve for X. If X is positive, it'll move to the right. If X is negative, it moves to the left. Yeah? So I just write there, if X is positive, it'll move right. If X is negative, it'll move left. Just to help you remember. Okay? And the last one, A. What does that do again? So we got up, down, which is vertical translation. We've got horizontal translation and horizontal stretch or dilation. What is A for? Artie. It is also dilation. Very good, but except this one is now vertical. So vertical stretch. And if you move your hands, you can see it's moving away from the x-axis. So dilation from x-axis. Now technically, both N and A, there is also one more I'm missing. If you have dilation, you have translation. What am I missing? Reflection. Reflection is only when you put a negative. So you can either flip vertically, so upside down, or you can flip horizontally, left or right. Yeah? So anything to do with vertical, so this is all the vertical side, so vertical dilation and vertical reflection. Whereas also here, the N also tells you reflection, but horizontal. So we say reflection in the y-axis, and this is reflection in the x-axis. And the way you sort of remember is like when you say reflection in x, it means where's the mirror. So if the mirror is horizontal, it flips upside down. Yeah? What's symmetrical is up and down. If the mirror is on the y-axis, then it's asymmetrical on left and right. So anything horizontal is here. Anything you do with the x is horizontal, so hence it flips left and right. If n is negative, flips up and down. If a is negative. Cool? All the transformations are still the same, so now you just need to know what the graph looks like. So on your page, I already printed out a graph for you. This is your typical log base 2 of x, or log base of anything graph. What are some key features? There are two key features that are pretty much the reciprocal of your exponential. Remember exponential, there were two key features. What are the two key features you need in an exponential graph? Name me one, Messi. asymptote. So exponential graph, remember when you sketch it, there should be a horizontal asymptote. Okay. What else is also prominent in an exponential graph? Lucky? Well, it doesn't touch the x-axis intercept because there's an asymptote there, but there is a y-intercept. What must the y-intercept be? So say if I gave you y equals 2 to the x, what would the y-intercept have to be? 0. Well, x is 0, but if x is 0, what's 2 to the power of 0? 1. All exponential graphs will fall under 0, 1 as your y-intercept. So here's an example. Whoops. It's this one. So just a refresher on the graphs. Here, 2 to the x. That's what it looks like, right? Notice where the y-intercept is. I'm going to change it to 0, 1 and label it. See that? 0, 1. So when x is 0, 2 to the power of 0 is 1. So it crosses the y-axis there, but it never touches the x-axis. Looks like it does, but when you zoom in, there's always a gap. So this is your exponential graph. Two properties. One is the asymptote, y equals 0. Let's make it a dotted line so that you remember. Let's do a dotted line. So there's a green dotted line there. That's y equals 0. And y-intercept is 0, 1. Now watch what happens when I change the base. Instead of 2 to the x, 3 to the x, 4 to the x, 5 to the x, 6 to the x. And notice those two properties don't change. The asymptote doesn't change. The shape of the graph did though. See, this was what 2 to the x looks like before. That's your comparison. That's 2 to the x. The larger the number, the steeper the line was. But the two properties, asymptote is still there, still gets really small, and it always crosses through 0, 1. That's providing that I haven't shifted the graph. If I shift the graph left, right, up, down, obviously it changes the y-intercept. But if I'm just taking it as it is, an exponential graph naturally will have 0, 1. So that means when you do the inverse, logarithms is the opposite of everything. So instead of y equals 0 as your asymptote, the horizontal is your asymptote. Now it's going to be vertical because you're flipping everything. The x becomes the y becomes the x. So then you'll get this shape. And notice you'll see this reflection. It'll look exactly the same but symmetrical. Yeah. So I'll show you. And how do you do it on Desmos? I'll show you how to do it. If you call that f of x, okay, that's the benefit of using function notation. That's 2 to the x there. If you want to type the inverse, you literally do this. X equals 2 y, which is, in our case, the function, f of x. So I want it to be f of, now instead of x, because it's not x anymore, because x becomes y and y becomes x, this now becomes f of y. Okay, so what I'm saying is, that is used to be your y value, so I'm saying y now becomes x, and what used to be the x now becomes y, so hence that letter changes to y. So I'm saying x equals f of y. That's why they're sketched, the inverse. All the properties that you had over here is now over here now. The horizontal becomes the vertical asymptote. Notice the graph gets closer and closer to the y-axis, but never touches. Notice that's at 0, 1, but if you flip it, if x becomes y and y becomes x, that point should be 1, 0. So if you have a look, I'll change that and I'll label it now, 1, 0. That's the logarithmic graph. So on your graph there, can you label the two key things? 1, it must have, not always, if it doesn't move the graph left to right, then it has 1, 0. But x-intercept is at 0, 1. And then the asymptote, which is now x equals 0. So beforehand, it was y equals 0. That's when it's the horizontal line. Now it's a vertical line, so it's x equals 0 is your asymptote. So you've got two key features. Asymptote, so it means that the log graph can never have a negative x value. And negative x will not exist. So if you tried log base 2 of negative 1, it won't work. So watch, I'll do it on a CAS calculator for you to see. If I did log, whoops, that's not it. Log base 2 of negative 1 comes up as error. Because logically, if you look at the graph, you never have x negative. It's always positive. Okay, you can't do log of 0 either, because 0 is undefined. You can do log of every other number. If you look at the graph, you can also see something that I haven't actually taught you yet to think about. But we did a bit of inequalities in our last session. notice here, between 0 and 1, what's the y values down here? They're positive or negative? Negative. And remember how we were saying, like, how do you get a log graph that's negative? Well, if I actually just did log base 2, but of a decimal, anything less than 1, so 0.3, for example. Whoops. See how it's negative? That negative is because I'm just looking at the graph. I just chose 0.3. 0.3 will give you a negative y value. So the logic to it is, if you think about the exponential graph, how do you get that? That means 2 to the power of this negative value will give you 0.3. And if you think about negative power, it's the reverse. It's the reflection horizontally. So the graph actually goes this way. Yeah? So 2 to the power of something drops down. Or you think about it this way, when it's negative power, negative 1 point something, the numbers drop. They get smaller for an exponential. Okay, so one of the hard parts is to link exponential and logs. Whatever happens here happens there, but just in the reverse. So it takes a bit of time to get your head around. Cool? All right, team. So let's fill in a couple of things. So you should have 2 things I want you to have in your notes. 1, log graphs have asymptote at x equals 0, and it has an x-intercept at 0, 1, providing it doesn't move left or right or up or down. Next thing, you guys learned domain and range from chapter 5. Looking at that graph, what's my domain? Ooh, close. I mean, 1 is here, but notice I still have this part of the graph as well. So it's not 1 to infinity. It is a subdomain, though. 0 to infinity. Now, 0 to infinity, you don't ever include the infinity, but do you include 0? No, because 0 is undefined. So make sure it's an open bracket. Out of curiosity, anyone remember, what's another notation for 0 to infinity, but don't include 0? R plus. Very good. You could actually do it this way. R plus means exactly the same thing. It doesn't include 0. So if you see in an exam, when they do R plus, what it means is it goes from 0 to infinity to the positive side, and it doesn't include 0. So if you want the 0 in it, you'd have to do union 0, meaning take all the positive numbers, also include 0, if you wanted the 0. In this case, this graph doesn't have a 0. So let's do R plus. Okay, just getting familiar with set notations and interval notation. What about the range? What's the range? So we can see the domain is all of these possible values here. So we said greater than 0. What else? What's the range? The range is the y-axis values. What is it, Mate? Yeah, that's it. I know the graph kind of looks like it kind of hovers here, but technically you can keep going. There's no cap. We'll just keep going, just at a very slow rate. Okay, so that's the logarithmic graph. So technically, what's another word or another symbol for negative infinity to infinity? Oh. Beautiful. So today's exercise, 13G, is about you sketching the graph, making sure you have these key properties in there. Okay, and 2 of which is axis intercept and the asymptote. If you can read left, right, up, and down, then you just make sure those 2 points match. Then it should be all right. Yeah, so we'll do some practice with that. Here we go. This is just me trying to remind you when you do it on Desmos why it is actually a reflection in that line. It's like the mirror is on the y equals x line, because every x value becomes y and every y value becomes x. So essentially they swap position infinitely. That's why it goes like that. Okay, so that's the exponential graph. That's the logarithmic graph. Yeah, one has a horizontal asymptote. The other one has a vertical asymptote. Cool? So this one never touches the y-axis, and this one never touches the x-axis. It looks symmetrical. Cool? So what did I write here? It is a reflection in the line y equals x. Okay, I'm saying there's a mirror on the line y equals x. That's where it flips. All right, let's do some practice. Flip over the page. Once you're ready, flip over the page, and let's do an example. Let's do this one. Wow. Put a whole bunch of transformations for you there. Let's break it apart. We've got f of x is equal to negative 2 times log base 2 of 6 minus 3x, close brackets, plus 2. Here we go. Let's do the easiest one. Plus 2. What does plus 2 tell me? What does plus 2 tell me? Let's go with Milena. What does plus 2 tell me? Up by 2. So this graph is going to shift up by 2. Now remember, a log graph normally looks like this. So if you shift it up by 2, the only thing that will likely change is that x-intercept. Because if you shift it up, then obviously this bottom bit touches the x-axis. Yeah, because you shift it up. But the asymptote should still stay the same. So asymptote is still currently x equals 0. And if I shift the graph up, then whatever's on the bottom will touch the x-axis. So the x-intercept will change. It means you have to calculate it later. Okay? Next one. So we got up by 2. Good. Let's look at the brackets. Now the technique I taught you to find out if it moves left or right. Here we go. Let 6 minus 3x equal to 0 and solve for x. That will tell you if it moves left or right. What does x equal to then? X equals to what? Can I please have? Let's go with Molly. 2. Because it's positive 2, that means it moves to the right. Now that does change the graph a bit. If I move the graph to the right, what feature in this graph will change? There are 2 things that would change actually, but one main thing. Yeah, the asymptote. The asymptote currently is at 0. So if you shift it to the right by 2, the asymptote would now be at 2. Okay, so when you draw it, make sure the asymptote's at 2. Okay, so I know already there is going to be a vertical dotted line at x equals 2, just because it tells me right by 2. I also know that the x-intercept is no longer 0, 1, because it went up by 2 and it went to the right by 2, something's got to change. Yeah, so already the graph with no negatives at the moment, that's what it should look like roughly. Don't sketch that. I'm just drawing it so you can visualize what's happening. Now we're going to look for any negatives. Notice the negatives. I've got a negative 2, but also there's a hidden negative that most students overlook. See that minus there? That's technically a negative in front of the x. So it's negative 3 times x at the moment. So I've actually did a hidden reflection there. Had that been a positive, then the graph wouldn't flip horizontally. But I did horizontal flip because that's on the x. And that's not on the x, so that's a vertical flip. So not only did I do a horizontal flip, I also did a vertical flip as well. So try to picture, what does that look like? I flip it horizontally, and then I flip it vertically. You guys picture what it looks like? Yeah? Okay, so roughly, hopefully in your picture, that's the horizontal flip. And then if you flip that upside down, it should look something like this. Okay, so what I'm picturing, something like that at the moment, roughly. Okay, don't sketch that. We're just picturing what it might look like. So I've got here vertical flip. I'm going to write here vertical flip, which is reflection. You also have horizontal flip because of the negatives. So that tells you the shape. So I now know the shape is roughly something like this. Then the last bit is any dilation. Dilation doesn't matter when you're sketching. It's good when you're describing, but when you're sketching, it doesn't matter because who knows what kind of dilation this is. I don't know whether it's thin, wide. It's just based on your scaling and based on your labeling. So I actually normally just ignore them, the 3 and the 2. The only time it matters is if you're sketching 2 graphs on one axis, then it does matter which one's steeper than the other. But that's much harder. So most examiners don't do that. Most examiners will not get you to sketch the dilation. They only need asymptote, x-intercept, y-intercept. So now we've got roughly the shape of the graph, but I don't know whether it looks like this or whether it looks like that or whether it looks like this. That's why you need to work out the x and y-intercepts to actually know which part of the graph. But I know x-intercept should be less than 2. Yeah, because based on the shape of the graph, x should be less than 2, and the y value could be anywhere. I just don't know where the y-intercept is. Yeah? So let's calculate it. Here we go. So we know the graph is meant to go somewhere in this direction. Let's work out y-intercept is the easiest one to work out first. How do you find y-intercept again? What do you have to do? Let x equal 0. So we don't know what y is, but we know on the y-axis, x is 0. So in your equation, what's your equation again? It was negative 2 times log base 2 of 6 take away 3 times 0 now plus 2. That's what you're trying to work out. So you're trying to work out what f of 0 is to work out the y-intercept. Here we go. Let's see. What's the y-intercept work out to be? So it's -2 times log 2 of, and 3 times 0 is 0, so that's 6 plus 2. Well, I don't know what log 2 of 6 is. That's like saying 2 to the power of what will give you 6. And at the moment, we don't have anything, so you can leave your answer like this. That's fine. Okay, so it means your y-intercept is, or if you want, you can bring the 2 up, but it really doesn't change the problem. So we'll just leave it as -2 log base 2 of 6 plus 2. That's your y-intercept. So when x is 0, it's a big, funky answer, log 2 of 6 plus 2. So you got 1 point. How do you find the x-intercept? What do you do? Y equals 0. So you don't know what x is, but you know the y value has to be 0. So that means now your equation is 0 is equal to -2 times log base 2 of 6 minus 3x plus 2. And this is what you've been training to do in the last exercise or the last 2 sessions. See if you can solve this. I'm going to pause the video.